Yeah, as I briefly mentioned, big our previous humanoid robots had big flat plates as feet, right? And those are good if you're doing position control on smooth, hard, even surfaces. But if it's not that kind of condition, then it's not good. As you can imagine, you have a rough surface and a rigid plate, your contact point is unpredictable and changes. So the recent generation robots, dynamic robots, you see a lot of point feet. And because it's a point contact, it's much easier to model. We wanted to do a little bit go beyond that, so we have pretty small feet. So our feet, do I have it here? It's the size of a finger or a pen, right? So we have two feet like this. So that was our original design, and we have a silicone molding case, or like a slipper over that finger-sized foot, and that's what we've been using. And then our result was, let me quickly show you some. Oh, by the way, I also have a lot of blooper videos that I have not shown. Let me see. The feet are very slippery. Let me show you it again. Right? They're slippery. So we decided to, one day, we said, shoes, athletic shoes, sneakers are designed for these kind of tasks. It's optimized for that. So why not just use sneakers? So we put on a sneaker. We just need to 3D print out a simple insert from that aluminum metal finger-sized foot to the foot shape. We just put it on, and it took us like a few hours. And we put a shoe on. It walks, and it walks much better. The grip is great, much more stable, much more faster. So if you've been in this field for bipedal locomotion, you probably know that every time you change the slightest thing, link length, mass property, something different, you have to change all the parameters, and you have to modify everything. It takes hours, if not days, to optimize everything. But Artemis was different. Change from a finger size foot to an actual sneaker, it's a huge difference, but we just put it on and it just works. So now Nike sends us shoes for free. So if you've seen our latest videos of Artemis is always wearing Nikes. Currently it's wearing the very popular Dunk Lows, right? You call it Pandas, the black and white Nike shoe. That's her favorite right now. But so we change shoes, and we don't change anything. We don't have to change any parameters. It just works. So before I'm a roboticist, I'm a loving father and a husband. That's more important. And, of course, I'm a roboticist. Doing research is important, but I would like to be remembered more as an educator. So in our lab, Romella, the Robotics and Mechanisms Laboratory at UCLA, of course, we build robots, we do research, we publish papers. But the most important outcome, the most important things from our lab is not our papers, not our robots, it's really our students. I want to build, I want to make the world a better place by pushing out great students that's going to be, leaders in the field in robotics and engineering.
Awesome. So we will talk about Artemis. I think that's the newest creation in your lab, and I think it's very cool.
Oh, yeah.
But before that, I want to ask you about what is missing in robotics. You have been now in the field, I think, a long time ago, and you see a lot of iteration. What's missing? What's still missing in robotics?
So most of the audience watching this or listening to this podcast, I believe, are in the field of robotics. And you might agree with me. Again, it might sound weird, but really everything, right? Robotics is such a integrated field that you need everything. And every time you have a breakthrough, you start to see that things are missing. For example, we actually built a lot of hardware prototypes that move, and they only last for 30 minutes. Of course, they have better energy sources. People are working on that. We also do a lot of leg locomotion, walking 2-leg, 3-leg, 4-leg, 6 legs. Because of that, we need better actuators. Most of the robots that use today, as you all know, use electric-based actuators are servo controls that does position control. We need better torque force control compliant actuators like proprioceptive actuators. We have new technology, but still we need different type of more biologically inspired actuators. We need better materials, lighter weight, more stronger strength to weight ratio. More computing power is always great. So again, we need everything.
So I want to go again. The most interesting part, I think, also in Artemis, the actuation, and you touched about the bear, artificial muscle resemble the biological artificial muscle. Can you tell us more about the design? And I think that's the most interesting part in the if we have artificial muscle resemble the biological one, that maybe shift the design paradigm. So tell us more about in Artemis, yeah.
Yeah, so again, most of the robots that exist today are stiff position control robots, the industrial robots. Most of the robots are that. These are great for precise motion, like assembly tasks. Those are great. However, when we want to have robots living and working next to humans, we need to have something more safer. Thus, we need to have compliant joints. And also for, especially for application where it goes through a lot of impact or contact, then we need these kind of biological characteristic actuators. Now, for the general public, I often use the term biological, artificial muscles, but that could be a little bit misleading. These are not really biology-based or chemical-based. Basically, these are proprioceptive actuators. As you all probably know, Professor Sang-bae Kim from MIT really started this revolution with the MIT Cheetah robot. Regular position servos are electric motors with a huge gear ratio gear output. So motors are really fast but very weak in torque. What we need to slow it down and increase the torque. Thus, we have these huge gearboxes or harmonic drives that like 200 to 1, 301 gear ratio that will up the torque and lower the speed. And that's great for position control. Proprioceptive actuator are a little bit different. We now have these higher torque motors. We call that pancake motors that has really high diameters. And then we do, the best scenario is to not have any gears at all. But of course, in reality, we need to have some kind of gears. So have 1 to 4, 1 to 6 gear ratio, really low gear ratio gearbox, and that's the output. So that's basically proprioceptive actuators. Now the advantage is because the gear ratio is so small, it's back drivable, which means that conventional servo motors, if you turn off the power, it doesn't move. It's stiff, right? So you cannot really do a torque control, a sense of torque from the motor side. If you have a very low gear ratio, then when you turn off the power, for example, then it's going to go flop down because it's back drivable. And if that's the case, we can use the current from the motor to do direct torque control, and that's the benefit. So if you use these kind of actuators, you can easily do torque control. It's great for impact mitigation. You can do so many things. You can change all the physical parameters just by software, and I think that's the best, the greatest advantage. There's some other approaches as well. As you probably know, hydraulics is one way to do something similar to that. Another way is we call that a series elastic actuators, which is basically a position called servo, and at the end we have a compliant spring or some kind of like a rubber, some kind of compliant element to it. So that's another approach. But we previously used a lot of series elastic actuators. But again, it solves a problem, but it creates another one. Like for example, the control bandwidth is really bad, very low. So there's still proprioceptive actuators is not the best solution. We need better ones. But at this point, I believe that's the best way to go with leg robots that goes through impact.
Amazing. So I want to go for your TED Talks. I think you highlight the evolution of the robot you design. It's really cool that you go for like balloon design and then you go to a humanoid robot. And I'm curious about your mind. It seems that like, yes, we have a problem. Let's shift it to a new idea and just coming back to Artemis, which we will cover. But can you tell us about the iteration and how it evolved in your lab? Let's go for design these whole days.
So I have a dream. In the future, I would like to be living with robots. Robots doing the dishes, taking out the trash. It's all great. But I claim that for robots to be living in our environment, the robot needs to be human shape and human size. And that's why we need human robots. Because if you look around, your stairs are a certain height for robots to walk up. Your door handle is a certain height for humans to open up. Or for robots to use tools, the robots needs to be human shape and size. And that's why we've been working on humanoid robots for a long time. So for the past 20 years, I've been working with humanoid robots. So these are some of the early humanoid robots that we designed. For example, this is called Darwin OP. You probably have some in your lab. It's an open source research education robot. Charlie is considered the United States' very first humanoid robot. Thor RD was used for the DARPA Robotics Challenge. Sapphire is a firefighting humanoid robot on Navy ships, and Thor and many different type of big and small robots. probably more than a dozen different type of robots that we developed in our lab. Now, however, these, we have a lot of problems. Like, we all know that they constantly fall down. They're slow. Of course, we now have technology that we can solve these kind of problems, but they're still very, very expensive. They're very complex, and I'm sure that you agree. They're very dangerous. You don't want to be next to these robots big robots moving around. But we need something. So from this, once I start to figure out, is there a way to make these bipedal robots solve all these problems? So this is your typical humanoid robot. So I found something really interesting. When the robot walks forward, one of the reasons why it constantly falls down is because the left and right leg has this distance, and because the legs go up and down and forward and backward. Because of distance, it creates this unwanted torque or moment. That's what falls down. So you probably have seen these, robot competition. This is called the Robo 1 competition, especially very popular in Japan. It's a robot fighting competition. But if you look at these robots, they are very fast and really agile, and they don't fall down. So if you look carefully, they walk sideways, because if you walk sideways, what happens? Your left and right leg, they line up, so your twisting moment disappears. I actually got this idea from watching TV. Fencing or ballet, they always walk sideways. So that was our thing, but the problem is you kind of use your knees. So let's change this, and we do this. Let's change the leg forward, and we constantly evolved it, and we have Nabi. You've probably seen this the video, so I'm gonna quickly just show this. But yeah, so this is Nabi, non-anthropic biped that walks like this. Let me, I don't want to use all of our time, so I'm gonna quickly go through. I'm gonna show you the actual robot. So again, a very simple change, just simply changing the orientation of the legs. Now we solve all the problems. It doesn't fall down. It's ridiculously simple. It's ridiculously stable. It can also jump and hop. We solved a lot of problems. But the problem is, this can walk forward and backward, but it cannot change directions, right? So what do? Then let's have two of these Nabis stacked onto each other, and that is called Alfred, Autonomous Leg Personal Helper Rotor with Enhanced Dynamics. So it can walk with 2 legs like Nabi. It can walk with 4 legs. It can change its configuration. It can do many things. So then we developed this actuator called Bear actuator that we just talked about. Back driver electromagnetic actuator robots. So we replaced the actuators for the Nabi with these. And now we have Nabi 2. Right? So this one can now not only walk, but also can hop and jump. It's great. So can do all these things. Let me show you some fun stuff. Like you've probably seen these meme video floating around. We're trying to do jump rope. Right, we have these fun stuff. So now it's time to change Alfred with this Bear actuator. So we have Alfred 2. Let me just quickly go past this and show you the actual video. So now it's really agile. It walks very fast and stable. It can hop and jump. It can walk with 2 feet. And when it's walking with 2 feet, it can use its other 2 limbs for picking up objects or doing fun stuff like this. Right? We talked about force control, so it can do knocking, which is actually kind of difficult, you might agree, as roboticists. But now it can hop and jump, and I guess we're having too much fun in the lab. Yeah, so this sort of shows our evolution of ideas. We have an idea, and then it's causing problems. How do we solve this? How do we come up with constantly creative ideas? But again, you can also use it for more a useful task. So this video is sped up, by the way. So you can walk with 2 feet, 4 feet. You can use its limbs for moving things. So yeah, these are some of the ideas, and we constantly innovate. Let me just show you. Of course, you've seen 6 legs robots. We also have climbing robots. Now we're interested in vertical mobility. So it can also not only vertical walls but also upside down. And we cannot not talk about Baloo. Let me just show you this. So this is a interesting problem. So can we actually solve this bipedal locomotion problem? As I mentioned, they're slow, they fall down, they're expensive, they're complicated. Is there a way to solve it? Yes, we can. And this is called Baloo Buoyancy Assisted Lightweight Leg Unit. Because we all know that robots always fall down, right? By the way, this is my son. This is an early version of Darwin OP that I brought home. So what if robots never fail? Or what if we can change the direction of gravity, which does not make any sense. But we ask ourselves these ridiculous questions, then ridiculous answers come out, which lead to innovation. So this robot Balu is a human-sized bipedal locomotion robot, but the body is a helium balloon. It's crazy. It's a balloon with 2 legs. So by the way, it's not lighter than air. It's still heavier than air, right? But it uses the buoyancy for stability. So, some might argue that this is not really bipedal locomotion because the legs are not really holding the body up. But nonetheless, it walks with 2 feet. So, hey, I call it bipedal locomotion. So, yeah, it constantly evolves. And you can go over and I can spend more than an hour talking about these robots. But I just want to show you that we come up with an idea. There's a problem. We try to solve the problem. From that, we come up with a different idea. And it constantly evolves. And I think so far, we developed more than 40, 50 robots in our lab. All different shape and sizes, morphologies. Yeah, so.
What did you learn from all these? Before going to Artemis, what is the common thing is that you learn? Because you have goals, be low cost, that's one of things, and energy and all these things. What you learn?
What I learned is this: there's always hurdles when you're doing research. I mean, if you know that there's a solution, we don't call that research. If you know there's a solution, we call that homework. Research is something that you do not know if it's possible or not, but you go for it, right? That is what we call research. So in our lab, we do not do our homework; we actually do our research. So we do not know if it's going to work, but we give it a try. And so many times I teach this to our students. So this is where I am, and I know my destination. I want to go there. Like I'm going hiking, right? Sometimes there's a big puddle of water, or there's a cliff that I have to go around. There's a huge, a mountain that it's difficult to climb, so go around. But you go around, and while doing that, even though I know my destination is over there, sometimes I find something new, something different. Or sometimes I find a completely different place that is actually better than the destination that I wanted to go to. Then that could be a better solution. So we're not afraid to challenge different things and try new things. And if there's a failure or things don't work out, that's fine. We take that. We learn from it, because if you have a failure, if you give up, then that's the end of the story. But if you use that as the learning experience, becomes a stepping stone for the success. And that's what we do in our lab. And that's how we come up with innovation.
Excellent. So I want to go to Artemis here. From your experience, we have now, that's I think the juicy part here, and also made the claims about the robustness. For example, if we see the Atlas by Boston Dynamics, I think it's really interesting that the claims you made.
So before starting, Artemis stands for, let me actually show you this. Artemis stands for Advanced Robotics Technology for Enhanced Mobility and Improved Stability. It's a humanoid robot it's the latest humanoid robot that we're very, very excited. So actually I have to be honest. I've been doing humanoid robot research for more than 20 years. And again, I truly believe, I always tell people that, I would like to have robots living in our, home. And to do that, I believe that robots to be human shape and size. However, if you asked me this question like 3 years ago, I would have said, yeah, that's still our goal. That's my dream. But there's a chance that this actually, possibly it's not going to happen during my lifetime, but we need to start now to make it happen sometime. So actually my expectation of when was very, very conservative. I thought it's going to happen really, really far in the future. However, with the success of Artemis and how it's performing, I'm starting to change my thoughts, and maybe the humanoid robots living with us is actually much closer than at least what I've been thinking. Artemis is a humanoid robot. It's a constant evolution for the past 20 years. From Darwin, Charlie, Thor P, Sapphire, all these robots. But this robot uses that proprioceptive actuator that I just talked about. So it's compliant actuation. It can run. It can walk 2.1 meters per second. Again, correct me if I'm wrong, but I believe this is the fastest walking humanoid robot in the world so far. Running, it might be the fastest running humanoid robot, but we just don't have enough space to test it. Just last week, we started to bring it outdoors in the UCLA campus in the soccer field, the track field, and we're starting to do experiments outdoors. But we believe that this might be the fastest running robots as well. But we're very, very excited. You mentioned about Boston Dynamics robot. Of course, Boston Dynamics Atlas robot. We all have seen it. It's the greatest. Everybody agrees that this is de facto the greatest, at this point, the greatest robot that exists today. But I make a bold claim that our humanoid robot could be a contender for Atlas. I'll carefully say that. Of course, Atlas robots uses hydraulics, so there's no way Artemis can be stronger, more powerful. However, in terms of speed of usability, maybe. Yeah, maybe. Yeah, but this robot can walk, jump, and moves boxes. You push, kick. You know, you've seen all those standard tests that you push. They walk on rubble pile. We take it outdoors on campus. It walks on, on the grass without tethers, by the way, and that's a big thing. Robotics, we all agree, doing robot experiments outdoors without tethers. That's a statement. So we're at that point right now.
Excellent. Maybe quickly about the hydraulic, because you mentioned hydraulic, and I think we had an episode with Bill Jackson, if you know him, the founder of the creator of Emika robot. But he said the hydraulic experience was pretty hot, and that's something I think advantage that you have beer actuator here. But another question about the noise also. How do you think about noise, since you need low cost and noise? But if you want to show the video first, then maybe you can discuss the noise and low cost. You can show the video first if you want.
Oh yeah, sure. Let me show you some. So let me show you an Artemis video. Okay, so you can see the stability. I'll show my face here too. So you can show the stability. If you see it, we're not babying it. We're actually kicking it. We're actually kicking it. All right. So sideways, for those who do, let me go back. For those who do bipedal locomotion, you probably know that sideways is more difficult because if you push it when the feet, they can't collide each other. But sideways, it's front and backward kicking disturbance is much more stable, but sideways is not bad. Again, we're pushing it, pulling it, and one more time, we're really trying to kick it. And my students, they quote unquote, they say, we cannot make it fall down, is what they said. And you all probably know RoboCup, the International Autonomous Robot Soccer Competition. So we are 5-time world champions in this competition, and this year we're going to Bordeaux, France with this robot. So we're toughing up with soccer as well. Let me show you some different. The 50 millimeter platform. It's not using perception right now, so it's just walking over it or on rubble pile. So again, even without perception, it's just using. So the point is that it's very, very robust. And again, let me show you. This video shows it's walking in our building. I think this was like 260 meters nonstop. It's autonomous. You can probably see let me show you. So this is the perception system. You can see how Artemis perceives the world while walking in the in the lab. Yep. So yeah, it walks up to 2.1 meters per second. That's what we reported in the lab. This is 1.2 meters per second. Let's up it 1.4 meters per second. It goes faster. Now look at my student who's moving the gantry. Now it's 1.6. Now he has to start to run or gallop. 1.8 and 2.1, and it goes faster and faster. It can also literally run. As you know, running means that there's a flight phase with 2 feet off the ground. Running is not yet that stable, so we still got a lot of work to do, but it does run without tethers. And again, moving boxes. By the way, it's an empty box, right? This is just to show the concept of this. It doesn't have any hands right now. Bigger boxes. We're having too much fun with this. What about pushing carts? Yeah, I can push carts. But this one, we just made it walk into the cart. We didn't do any different type of behavior, right? And now again, you would agree this is a big claim, right? Using bipedal robots outdoors without any cables or tethers. This is a big statement. And we do this every 2 weeks minimum. So we bring it outdoors in the to campus, and students come and they greet and meet the robot, and they take selfies. It's a lot of fun too.
That's really impressive. Maybe I want to go for the leg design, because you mentioned in leg design, you mentioned that optimization and how you come up with the shape of the leg of design. Can you tell us about the optimization here?
So let's start with the easy stuff first. Of course, the audience are roboticists, but you probably all know this. But generally, for the layperson, the general public, when I talk about bipedal robots, they constantly falling down on the instability. general public or regular, the lay person might think that, oh, why don't you lower the center of gravity and make the feet heavy? Then it's going to be stable. Or they might say, oh, why did you make the foot so small? By the foot is the size of a finger for Artemis. But by the way, we do now have shoes, by the way. And then why don't you make the foot really big? Wouldn't that make it stable? That's true if it's a static structure, but this is a dynamic moving robot. And for these type of bipedal robots, you want to have the distal, the further away from the center of gravity, closer to your foot, you want to make it lower mass as possible, because the part that's really moving when you move your legs, and these are the feet, you want to have the feet as light as possible. So we try to reduce the mass and try to bring the center of gravity towards your belly button, so to speak, right? So to do that, we have different techniques. For example, typically a humanoid robot leg, a single leg, has 6 degrees of freedom. Most all humanoid robots do that. But Artemis, we have 5 degrees of freedom. We intentionally gave up on 1 degree of freedom, and that's the roll of the ankle. So the foot only has pitch, it doesn't have roll, which is, I think, is okay for what we're trying to do. The reason why we got rid of 1 degrees of freedom is because we want to reduce the mass, distal mass, and also we're trying to pull most of the heavy things, which are the actuators, towards the center. So if you look at the hip, let me actually show you over here. If you look at the hip, you see that this big disc right over there, right? Those are the big bear actuators. Now you can see 2 for the left hip and 2 for the right hip. One is for the leg pitch. The other one is actually for the knee. So we have a linkage system to bring the actuator for the knee up towards the hip. Same thing for the pitch for the ankle. We move it towards the knee. So we try to move heavy stuff upstream, so to speak. And also the link design. And let me show you if I have a cool video of that. All right, so yeah, let me just show you from here. Okay, so you can see, because this is a brand new technology, you cannot buy components. So every single piece we design and build in-house. So this is our 5-axis CNC machine. We cut our own gears. We design our power electronics, motor controllers, everything except for bolts and nuts, cameras and computers. We design everything, including our foot contact sensor. But look at the part. This is art. I find this sexy. Now, the reason why these parts look so organic is because we use topology optimization when we design things. Look at this part. This is the femur, right? Yeah. So what we do is in the computer CAD, first of all, we give all the possible the boundary volume of the part can go into, right? And then based on that, we give all the loading conditions, and the computer spits out a optimized topology, and based on that we do iteration. And result of that is this the links that looks very organic, and works perfectly. It's the lightest weight for which can handle the loading conditions. So we're very happy and very proud. Look at that, beautiful, right? Look at that. Love it. Again, I can go on and talk more,
But big question about the shoes. Why did you choose to have a shoe in the robot? Is it a reason for that?
Yeah, as I briefly mentioned, our previous humanoid robots had big flat plates as feet, right? And those are good if you're doing position control on smooth, hard, even surfaces. But if it's not that kind of condition, then it's not good. As you can imagine, you have a rough surface and a rigid plate, your contact point is unpredictable and changes. So the recent generation robots, dynamic robots, you see a lot of point feet. And because it's a point contact, it's much easier to model. We wanted to do a little bit go beyond that, so we have pretty small feet. So our feet, do I have it here? It's the size of a finger or a pen, right? So we have two feet like this. So that was our original design, and we have a silicone molding case, or like a slipper over that finger-sized foot. And that's what we've been using. And then our result was, let me quickly show you some. Oh, by the way, I also have a lot of blooper videos that I have not shown. Let me see. The feet are very slippery. Let me show you again. Right? They're slippery. So we decided to, one day, we said, shoes, athletic shoes, sneakers are designed for these kind of tasks. It's optimized for that, so why not just use sneakers? So we put on a sneaker. We just need to 3D print out a simple insert from that aluminum metal finger-sized foot to the foot shape. We just put it on, and it took us like a few hours. And we put a shoe on. It walks, and it walks much better. The grip is great, much more stable, much more faster. So if you've been in this field for bipedal locomotion, you probably know that every time you change the slightest thing, link length, mass property, something different, you have to change all the parameters and you have to modify everything. It takes hours, if not days, to optimize everything. But Artemis was different. Change from a finger size foot to a actual sneaker, it's a huge difference, but we just put it on and it just works. So now Nike sends us shoes for free. So if you've seen our latest videos of Artemis is always wearing Nikes. Currently is wearing the very popular Dunk Lows, right? You call it Pandas, the black and white Nike shoe. That's her favorite right now. But yeah, so we change shoes and we don't change anything. We don't have to change any parameters. It just works.
Now, this is really brilliant. Yeah. Maybe another question about the noise and energy. Maybe about the noise, because we speak about the Atlas robot and it's a pretty hard experience to use hydraulic, but also noise. What do you think about the noise here, elements?
Yeah, so again, one disclaimer. Of course, I'm a mechanical engineer. I know about a lot of things, including actuations, and that's my field of study. But I have to disclaimer is that I actually personally have never used an hydraulic system or developed a robot using hydraulics. So my experience and knowledge is based on what I've learned and what I've seen with my colleagues working with hydraulic systems. So with that disclaimer, hydraulic systems at this point, if you want power, hydraulic system is the way to go, because you cannot, electric-based system still cannot beat in terms of power density hydraulics, and I believe that's why Boston Dynamics is using hydraulics. They have their new type of hydraulic motors, which are fantastic. But again, with my understanding, for hydraulic systems, you need to have, it becomes very difficult to design and package. You need to allow this plumbing, you need to have an accumulator, you have to have the compressor, and this compressor is very, very noisy. Energy efficiency is also a problem. So it has its own share of problems. It's also very messy. It's very difficult to avoid leakage for a hydraulic system. So it's not that practical for indoors use or next to humans. But again, if you look at outdoors, your crane and these excavators, they use hydraulics, so still it's good for outdoor, like big messy stuff. It's still fine. But my goal is to have robots living with us in this human environment. Thus, we want to go with magnetic, basically electric motor-based system. So that's what we're doing. If you've seen some of our Artemis robot videos, a lot of people ask us this question. Wow, it makes this like every time we watch, we're like clack, 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 clack sound. And because our robot videos are very fascinating, once you start watching, you cannot take your eyes off. So in your head, it constantly, even after you turn off the video, you constantly hear this click, click, click sound. Now that a lot of people think that click, click sound is from the feet hitting the ground, but that's not the case. The feet hitting the ground, that's fine. It's really the bare actuator, because it's a rotary actuator. It needs to really nearly instantly change the direction, and that's from the backlash from the gear. It needs to go like clack, clack, clack. That's where the sound happens. Again, because we designed and we manufactured all the gears in-house by ourselves, it cannot be perfect. So I think that's where we can make improvements. But again, the sound, for me, it's like music. I like it. Yeah. But again, it's not from the feet hitting the ground. It's from the gears instantly changing the direction. So that's the sound. Noise issue.
Interesting. So
we dance to the beat, like. Yeah.
I know we don't have so much time, but I will ask you the question: what are the next steps for Artemis? What's your next plan or improvement?
Sure. Many things. Again, I made some bold claims, and I talked a lot about Artemis. Again, truly, that's what I believe. It's great. I think this is the direction. This is the beginning of something great. I truly believe that. But still, we have a long way to go. We are actually pretty much satisfied with the walking locomotion. I think it's stable enough to be used safely in public spaces around people. I mean, that's why we bring it out in the campus and things like that. But we want to break the Guinness World Record in the fastest running humanoid robot, and we believe it might already be fast enough to do that. We just haven't tested it, and running compared to walking, it's not that stable enough to do that. So we want to do that just so we can break the world record. Haha, that would be fun. But it is going to fall. So because it's going to be, it is going to fall. We want to make it, when it falls, we want to make it fall safely. There's a lot of techniques and things technology that we're thinking about. And once it has fallen, it needs to stand up on its own. So we're also looking into that. Mechanically, of course, it's designed to do parkour, jumping and flipping. Mechanically, it has the power, the strength to do all these crazy hyperdynamic locomotion. But again, it's gonna take time to actually utilize the full power of it. We're still using less than 40% of its power, so we still can do a lot of things. The robot, again, has the mechanical ability to climb upstairs, but we have not implemented that yet, so climbing upstairs would be something that we want to work on. It does have an upper body, the arms and head moves, but the arms are not really being used. We do try to do counterbalance for stability, but it turns out the arms, the inertia is so low, it doesn't have much effect, so that's not useful. But it's not designed for manipulation, or I would say our focus is in the locomotion right now. Manipulation is not our current focus, but yeah, of course, if you want to have these robots do real, useful tasks, it needs to do manipulation. So as you've probably seen, the robot does not have any hands, so probably gonna put on hands. By the way, we do have many hands developed in-house. That's pretty impressive. But we are not going to put hands on Artemis until we believe that we can use these hands in a meaningful way. Okay, we can put hands right now. It's gonna do all these things, but we don't think it's ready to do meaningful manipulation. So manipulation comes probably later. That's not our current focus. But again, besides, even with these just rubber ball things, you can pick up boxes and move, and that's pretty cool for me. Yeah, but more of an immediate goal, as I mentioned, this July, 2023 July, RoboCup, the International Autonomous Robot Soccer Competition, we're going with Artemis. So we're very excited. So we're testing things. So our immediate goal for the next few months is just putting all of our effort in, make sure these robots kick, run, do all the, I'll save for the next interview or for our next podcast. I'll save the soccer stuff for the next one. Yeah.
You mentioned that you want robot not to fail. For example, it's already could fail and how to self-right itself. But how you imagine robot to be more robust in failure, like failure and also falling, also both, and also safety component yeah.
So there's two things. One is if it falls, how to make it fall safely. And before that is try to make it not fall at all. So there's two different approaches. Try to not fall at all is what we're trying to do. Try to make it robust, resistant against external disturbance and things like that. We've been working on that. And again, as I mentioned, we're pretty happy with where we are. I don't know if you saw in the video, but when it walks autonomously, when it went through the door, the very narrow door to our lab, it actually bumped its shoulder on the door, the wall, and it was perfectly fine. And you've seen us push on everything. So we're actually very happy with resistance against disturbance. But now we want to focus on how to make it fall safely. Of course, think about humans, right? When you think then there's many different techniques that we just use use or something like, whoa, use your arms like a flywheel. Or sometimes when you slip, you jump or actually take a big step like that to rebalance yourself. Or sometimes you cannot do anything, then you just don't, like most of the E-stop switches just cut the power, but that's not how it should be. An emergency, it should have the damping mode, so you actually fall down slowly. Or when you slow down, when you fall down, you probably can tuck in your body like this, or possibly brace yourself. So there's many different techniques or many things, many approaches that we can employ and use, and those are some of the research tasks that we want to do.
Mm-hmm. Excellent. Maybe a quick question, because I know we don't have so much time, a few minutes. The humanoid robot markets now, because now there's a lot of interest in the market. I'm curious, how do you see, and I know that you have been involved before, but I don't want to talk since you are not comfortable about that. But I want to ask you, since you now have Artemis and the market, and there's a lot of competitors now released humanoid robots. So tell us.
Yeah. So, yeah, it's a little bit sensitive topic for me to publicly say things because I might or might not be involved with a certain company and things like that. But as I mentioned, if you asked me 3 years ago, I would say like, oh, humanoid robots doesn't make any sense as a market right now. They're still dangerous. They're expensive. All the things I talked about, they fall down. It doesn't make any sense. But now I'm starting to change my thought a little bit. But still, as a product, I'm not sure. I mean, a lot of smart people, successful business people are starting, you probably know, Boston Dynamics is more like a research long-term project, but Tesla is actually doing it. Figure.ai, Figure, you probably know. Aptronics, there's many. Agility Robotics, which actually have the highest respect for their work as well. There's many other companies. These are all smart business people as well. So I guess there is a business case. I'm not exactly sure, but at least technology-wise, actually, we're actually getting close. But just because your robot can do all those tasks does not mean it's going to be a successful business. But I'm not an expert in the business side, so I'll leave it there.
And do you think that every human should have a humanoid robot? Since your vision or your dream that we have a humanoid robot at our home, do you believe that everyone should have a humanoid robot?
Depends when. Today, absolutely no. I don't trust our robots. I don't have any robots out of my home. I don't trust our robots. Way in the future, without giving me a year or something like that, well, if the robot is really stable and is useful and is economically makes sense, then yeah, why not? We all know that we build robots for what? The 3Ds, the dull, dirty, dangerous. Things that humans shouldn't be doing or cannot do or don't want to do, let the robots do it. And as I mentioned, humanoid robot form is the most general form. So why not have a humanoid robot at home and make it do all the things that we don't want to do? So the answer is yes, when we have these type of robots, which is probably still a long way to go.
Mm-hmm. One question about MasterChef, then, so you have also activities beyond the academia and research. Do you also think about robots? Then, so you see robots in the kitchen and you have this experience. Can you just quickly?
Yeah, so just for people who don't know me, I'm also a hobbyist, a pretty serious gourmet chef. When friends and family come over, I do like 8-course degustation menu. I was on MasterChef USA season 4 as well. Don't look it up; it's kind of embarrassing, but I was actually on there. So I do a lot. I cook every day at home, by the way. So there are great chefs in the world. There are great roboticists in the world, but there's not a lot of good chefs who are also roboticists. I'm one of them. Thus, I haven't really talked publicly about it, but we do have a pretty big multi-million-dollar project for a cooking robot funded by a Korean company. But we're not supposed to tell too much about it, but I can say that the project is called Project Yori, Y-O-R-I. It's not a single-tasker cooking robot. Theoretically, it can cook anything. I'll just put it that way. And it doesn't cook like humans. Because most of the robots that you've probably seen, they try to mimic how human. This robot even doesn't even have hands, and it uses. Yeah. Hopefully, again next year when you do another podcast, I'll be able to show, or I'll invite you over. You probably want to have some your lunch. The robots will be cooking lunch for you. How's
so
that?
That's a promise. That's a promise. I'm in. So
I'm not a promise because you don't know if we're going to be successful. I'll say it's a wish. Sounds good?
Yes. So, any final words to people listening? Just we're closing now. So, any final words you'd like to say for people?
Yeah. So, this is just for more of the younger generation of the general public. I know that most of the people here are roboticists, but again, I started when I was 7 years old. This is a true story. I watched the movie Star Wars, the first one, Episode 4, for the first time in the Man's Chinese Theater. All the lightsabers and all the spaceships completely blew me away. But in the movie, the two droids, they call it droids, the R2D2, the one that looks like a trash can, and C3PO, the humanoid robot, completely blew my mind. And on my way home in the car, I told my mom and dad, I want to grow up to become a robot scientist. And I followed my dream, and I'm here today. So, follow your dreams. That's what I'm doing. I'm not the richest person in the world, but I can, safely say that I'm probably one of the happiest person on this planet. So follow your dreams.
Thank you so much, and it's just a great honor talking to you, and I really appreciate it. Thank you.
Yeah, next time, do come to our lab. You should meet and see our robots walking, jumps, and rollings. It's a robot zoo. It's fantastic here.